And then there are the forces. So there are three forces in our kind of quantum description of the world. We don't include gravity. We don't know how to deal with that yet. We don't include gravity. We don't know how to deal with that yet. We don't include gravity. We don't know how to deal with that yet. Lots of reasons, mostly to do with astronomy, actually, thanks to you and your colleagues discovering this inconvenient stuff out there in the universe called dark matter. So that suggests there must be more stuff that we haven't found yet.
Interesting.
Yeah, whatever dark matter is, we have no idea. And maybe these guys will find it in their particle accelerator.
Right.
And if they do, we'd be very happy, because right now it's just this term in our equations.
Right.
It's like,
but we know it's something.
Something's there.
Something's there.
And so we throw it in the equation.
Right.
And let somebody else figure out what the hell it is.
What the something is. What about dark energy, though? Because that's not a particle.
Well, we don't know.
Harry,
Harry,
I'm going to throw this one over to you, Harry.
I mean, yeah, no, we have no idea, right? We have absolutely no idea. I think it's fair to say. I mean, this is when particle physicists try to talk about dark energy, things go really badly wrong. So I should be careful. But there was this one idea for what dark energy is what we call vacuum energy. So it's the energy left over in empty space once you've taken away everything else, all the atoms and all the particles. And in particle physics, the actual truth is that particles aren't really the fundamental ingredients of the universe. They're actually made of something more fundamental, which is called a quantum field. So for all of these 17 particles we talked about, there is a corresponding field, and the particles are actually like little vibrations in that field. They're like ripples in an ocean, if you like. So those fields, even when you've got rid of all the particles, they're still there in the vacuum. And if you take, the idea was that maybe dark energy is all the kind of quantum fluctuations that's left over in these fields in the vacuum. But if you run the numbers, you get an answer that is 10 to the power 120 times too big. So that's 10 with 120 zeros at the end, which is like a ludicrously enormous number. If it was that big, the universe would be ripped apart in an instant. So we have no idea what's going on, really, from a particle physics point of view.
Mm. So it's the biggest discrepancy ever between a theory and an observation. Mm. So it's the biggest discrepancy ever between a theory and an observation. Mm. So it's the biggest discrepancy ever between a theory and an observation.